Welcome once more to our peaceful exploration of the wonderful realm of numbers and logic. I'm delighted you've joined me tonight, wherever you find yourself in this moment. Maybe you're nestled comfortably in your bedroom with a gentle lamp creating dancing silhouettes on well-known walls, or perhaps you're settled in a cherished armchair as evening draws closer, the burden of daily worries slowly melting away from your mind. There's something wonderfully soothing about discovering boundless concepts while we ourselves are limited creatures, searching for both peace and knowledge in equal portions. Numbers, in their truest essence, provide us with a form of contemplation, a method of reasoning that rises above the immediate and the utilitarian, pulling us into domains where logic unveils designs of remarkable elegance and unforeseen balance. If these numerical wanderings prove useful for your relaxation, I would be deeply thankful if you showed appreciation by liking this content or joining me for additional journeys into the graceful riddles that have fascinated human consciousness for ages. There's something about numbers that appeals to our most fundamental longing for structure and significance, a dialect that explains not merely how things exist, but how they absolutely must exist. Tonight's adventure will guide us through territories of thought where the unthinkable becomes ordinary, where our most basic beliefs about magnitude and amount dissolve into something much more sophisticated and astonishing. We'll learn that boundlessness isn't simply an enormous figure, but a completely distinct type of numerical entity that follows its own unique calculations. This evening, we're about to enter one of the most charming mysteries in all of numerical study, a mental exercise so appealing and puzzling that it has been captivating learners and experts equally for almost 100 years. We'll examine Hilbert's endless lodge, named after the exceptional German number theorist David Hilbert, who initially suggested this puzzle in the 1920s during an era when mathematicians were still grappling with the unusual characteristics of boundless collections. But our expedition won't end there. Like voyagers who find that each stop reveals fresh horizons, we'll uncover how this apparently straightforward accommodation reservation dilemma opens pathways to deeper maze about the essence of boundlessness, the groundwork of numerical study, and the actual way we comprehend existence itself. Throughout our path, we'll encounter additional numerical ideas that hover around the borders of the boundless, each contributing another dimension to our grasp of how mathematicians consider endless opportunities. We'll meet mysteries that have confused brilliant minds, principles that reshape our comprehension of what's achievable, and methods that expose the hidden framework underlying apparent disorder. Numbers are filled with such surprises, instances when careful logic guides us to findings that appear to oppose common understanding, yet turn out to be not just accurate but meaningful. These meetings with numerical strangeness have a way of broadening our minds, teaching us to perceive beyond the constraints of direct experience. Before we register at our unusual establishment, let me provide the gentle notice that this examination is meant for learning and calm. While we'll be handling some deep numerical ideas, there's no burden to grasp everything flawlessly. Sometimes the pleasure is simply in the pondering, in allowing these concepts to flow over you like a soft wave, washing away the built-up stress of the day. Numbers, at their core, are about designs and beauty, about the deep contentment that comes from seeing how apparently unconnected concepts fit together in graceful and surprising ways. Tonight we'll discover designs so unusual and beautiful that they seem to twist the very foundation of logic itself, yet show themselves to be as natural and unavoidable as the changing of the seasons. Imagine, if you would, a most peculiar lodge, not the kind of place you'd discover along a roadway or in a busy downtown area, with its familiar building style and comforting boundaries, but something far more remarkable. This lodge extends endlessly into the horizon, its chambers numbered 1, 2, 3, 4, and going on eternally like a numerical sequence made real in stone and wood. There is no highest chamber number, no final entrance at the conclusion of a corridor, no uppermost level where the lifts stop and tired travelers must finally accept the limits of their journey. The structure reaches beyond the skyline, beyond any imaginable endpoint, into a distance that has no meaning in terms of physical measurement. This is Hilbert's Lodge, a building that exists not in our physical realm but in the domain of numerical thought, where the impossible becomes merely puzzling and the absurd reveals deep truths about the nature of boundlessness itself. Here, in this imaginary establishment, we can explore questions that have no meaning in the limited world of our everyday experience. What occurs when something that's already complete tries to welcome something additional? How can space be formed where none exists? What does it mean for something to be occupied when it has no limits? These questions might seem like philosophical riddles, but numbers provide precise answers that illuminate the deep structure of logical thought. The lodge appears normal enough at first sight, with its welcome counter and baggage trolleys, its uniformed workers and familiar conveniences. Each chamber has a number on its entrance, starting with Chamber 1 and proceeding in the familiar sequence we learned as children. The hallways are well illuminated and comfortable, the chambers furnished with all the necessities a traveller might need. But unlike any lodge in our experience, these numbers continue without end, stretching through the millions, the billions, the trillions, and far beyond into numbers so large they dwarf our everyday experience, yet remain as natural and inevitable as the numbers we use to count our pocket change. Yet each chamber is perfectly real within our numerical thought experiment, each capable of housing a visitor for the night, each as substantial and meaningful as any chamber in any lodge you've ever visited. The building itself defies physics, of course, requiring neither materials nor energy in boundless quantities, sustained by no economic model that makes sense in our familiar world. But numbers are wonderfully free from such earthly constraints, liberated from the practical concerns that limit our physical constructions. Here, in the realm of pure thought, we can construct objects that illuminate the deepest properties of number and boundlessness, free to explore the logical consequences of our assumptions without worrying about whether concrete and steel could actually support such impossible architecture. Our tale begins on a particularly crowded evening at the Endless Lodge, when the establishment finds itself in a situation that would spell disaster for any conventional accommodation. Every single chamber is occupied, every bed filled with a content visitor, from Chamber 1 with its view of the numerical gardens to Chamber 1,000,000 with its panoramic vistas of boundless possibility, and onward through all the countless chambers that stretch beyond any finite enumeration. The visitors are diverse, representing every conceivable type of numerical traveler, number theorists exploring the properties of primes, geometrists investigating the nature of space, analysts studying the behavior of functions, each finding in the lodge's boundless expanse a perfect reflection of their own unlimited intellectual curiosity. This might seem like a problem for any new arrivals, the sort of situation that in the limited world would require turning away disappointed travelers, or perhaps offering to put them on a waiting list for the next available vacancy. But the night supervisor of the Endless Lodge is no ordinary person, shaped by years of working in this most unusual establishment. He has learned to think in ways that transcend the limitations of finite arithmetic, to see possibilities where others see only constraints. He understands something that most of us find difficult to grasp, something that goes against our most basic intuitions about how quantities behave, that boundlessness plus 1 still equals boundlessness, and more remarkably, that this equality is not just a numerical abstraction, but a practical principle that can be applied to solve real problems within his boundless domain. When a weary traveler arrives at the front counter in the quiet hours after midnight, asking for a chamber with the resigned expression of someone who expects to be told that no accommodation is possible, the supervisor doesn't turn him away. Instead, he reaches for the lodge's public address system, that miraculous network that can reach every chamber in the boundless establishment simultaneously, and prepares to make an announcement that would sound absurd in any finite establishment. His voice, calm and assured, carries to every corner of the boundless building. Attention visitors, we hope you're enjoying your stay with us this evening. We need everyone to move to the chamber whose number is 1 greater than your current chamber number. We apologize for any inconvenience, and of course there will be no charge for this minor relocation. The request seems impossible to fulfill, defying every principle of logic that governs the limited world. After all, where can the visitor in the last chamber go? Every chamber is occupied, every space filled, and adding even one more visitor should be numerically impossible. But here's the beautiful mystery that lies at the heart of our story. There is no last chamber. The boundless sequence of chambers has no final member, no ultimate destination where the migration must come to a halt. In the strange arithmetic of boundlessness, every visitor can move to a new chamber because there's always a chamber beyond any chamber you can name, always a next number beyond any number you can specify. The visitor in Chamber 1 gathers his belongings and moves to Chamber 2, finding it exactly as comfortable as his previous accommodation. The visitor in Chamber 2, now vacated by the first visitor, moves to Chamber 3. The visitor in Chamber 3 moves to Chamber 4, and so the pattern continues, creating a perfectly coordinated dance of boundless proportions that unfolds simultaneously across the entire establishment. Each visitor has a new chamber to move to. Each migration happens smoothly and efficiently, and when the great relocation is complete, Chamber 1 stands empty and ready, waiting to welcome the new arrival with the same comfort and hospitality that every other visitor enjoys. Not a single existing visitor has been displaced or inconvenienced beyond the minor effort of changing chambers. Indeed, each visitor now occupies a chamber with a number 1 higher than before, a change that makes no practical difference in an establishment where all chambers are equally comfortable and well appointed. Yet somehow, through this collective migration, space has been created from apparent fullness, possibility extracted from impossibility. This is our first glimpse into the strange arithmetic of boundlessness, where our intuitions about limited quantities begin to break down in the most elegant and surprising ways, revealing logical structures that seem to transcend the very foundations of ordinary reasoning. The night supervisor watches with satisfaction as this impossible choreography unfolds throughout his boundless domain, visitors moving with practiced efficiency through hallways that stretch beyond any conceivable horizon. In a limited lodge, such a request would be absurd, a logical impossibility that no amount of clever thinking could resolve. Ask every visitor in a fully occupied limited lodge to move to the next chamber, and you'll inevitably reach a visitor who has nowhere to go, trapped by the fundamental limitation that limited sets have final elements. But in the boundless realm, what seems like an insurmountable problem becomes a routine accommodation, as natural and straightforward as any other aspect of lodge management. This shift of perspective represents something profound about numerical thinking, the willingness to extend our familiar concepts into realms where they behave in unexpected ways, to follow logical reasoning wherever it leads, even when it contradicts our immediate intuitions. The supervisor understands that boundlessness is not just a very large number, but something qualitatively different, a concept that requires us to abandon some of our most basic assumptions about how quantities behave. It's not that the rules of logic have changed, but that we're applying those same rules in a context where they reveal possibilities that simply don't exist in limited situations. He has learned to think like a number theorist, to see possibilities where others see only impossibilities, to find patterns and structures that remain hidden until viewed from the proper perspective. This kind of thinking requires both rigorous logical discipline and creative imagination, the ability to follow complex chains of reasoning while remaining open to conclusions that challenge conventional wisdom. Numbers reward this combination of precision and creativity, offering insights that are both logically necessary and genuinely surprising, both rationally compelling and aesthetically beautiful. News of the lodge's remarkable flexibility spreads quickly through the numerical community, carried by word of mouth among scholars who find in this thought experiment a perfect illustration of principles they've been studying in abstract form for years. Soon our establishment faces an even greater challenge, one that tests not just the supervisor's understanding of boundless arithmetic, but his ability to scale his solutions to handle larger and more complex situations. A tour coach arrives at the lodge's entrance, its headlights cutting through the numerical twilight, carrying 40 enthusiastic number theorists who have heard about the lodge's unique properties and wish to experience them firsthand. These travelers are not ordinary tourists but scholars and researchers who have spent their careers studying the properties of boundless sets, the behavior of numerical functions, the deep structures that underlie all numerical reasoning. They come seeking not just accommodation but insight, hoping to experience firsthand the strange arithmetic they've studied in textbooks and research papers. For them, the lodge represents more than a place to stay. It's a laboratory where abstract numerical principles take on concrete form, where the theoretical becomes experiential, where ideas that might otherwise remain trapped in the realm of pure abstraction can be felt and lived as well as understood. Once again, every chamber in the lodge is occupied, filled with the previous evening's visitors who have settled in comfortably and show no inclination to leave their numerical paradise. Once again, what seems impossible in the limited world becomes merely interesting in the boundless realm. Another puzzle to be solved through the systematic application of logical principles. The night supervisor, now growing confident in his understanding of boundless arithmetic, sees the arriving coach not as a problem but as an opportunity to demonstrate the scalability of his methods, the way that solutions to boundless problems can be extended and generalized to handle even more complex situations. He approaches the public address system once more, his voice carrying to every corner of the boundless establishment with the calm authority of someone who has learned to work within the strange logic of boundless sets. "Attention visitors," he announces. We hope you're continuing to enjoy your stay with us. We have a coach of distinguished numerical visitors who would like to join us this evening. We need everyone to move to the chamber whose number is 40 greater than your current chamber number. As always, we apologize for any inconvenience, and this relocation will be provided at no charge as part of our commitment to advancing numerical understanding. The solution follows the same pattern as before, but with a larger shift that demonstrates the scalability of boundless arithmetic. The visitor in Chamber 1 moves to Chamber 41, carrying his luggage through hallways that accommodate his migration with boundless patience. The visitor in Chamber 2 moves to Chamber 42, the visitor in Chamber 3 to Chamber 43, and so forth in a coordinated migration that spans the entire boundless establishment. This carefully orchestrated movement leaves the first 40 chambers vacant, creating exactly the right amount of space to provide perfect accommodations for the arriving number theorists, each of whom can now enjoy the same level of comfort and service that the lodge provides to all its visitors. What's particularly beautiful about this solution is how it scales naturally and effortlessly, whether the coach carries 40 passengers, 400, or 4,000. The same principle applies with numerical precision. Any limited number of new visitors can be accommodated through an appropriate shifting of existing visitors, a testament to the strange arithmetic properties of boundless sets. The solution doesn't become more complicated as the numbers grow larger. It simply requires adjusting the shift parameter to match the size of the arriving group. This scalability reveals something important about the nature of boundless quantities. They're not just very large limited quantities, but something categorically different that obeys its own distinctive rules. This scalability reveals something important about how number theorists approach problems, something that distinguishes numerical thinking from other forms of problem solving. They look for patterns and principles that can be generalized, that work not just in specific cases but across entire categories of situations. The Knight Supervisor's solution isn't just clever, it's systematic and extensible, embodying principles that remain valid regardless of the specific numbers involved. He has discovered a method that can handle any limited influx of new visitors, no matter how large, demonstrating the kind of general solution that number theorists prize above all others. This kind of generalization is central to numerical thinking, the ability to see beyond particular instances to underlying structures and principles that govern entire classes of problems. When a number theorist solves a specific equation, they're usually more interested in the method than in the particular answer, because the method might apply to boundlessly many similar equations. When they prove a theorem about triangles, they're seeking insights that illuminate the nature of all triangles, not just the specific examples they happen to examine. This drive toward generality and abstraction might seem removed from practical concerns, but it's actually what makes numbers so powerful and widely applicable. But even as our Knight Supervisor grows comfortable with these limited challenges, confident in his ability to accommodate any limited group of new arrivals through systematic application of shifting techniques, the lodge faces its most perplexing situation yet. As he gazes out the front windows during the quiet hours before dawn, checking on the numerical landscape that surrounds his boundless establishment, he sees something that makes even his numerically trained mind pause in wonder. Approaching the lodge through the morning mist is a coach of impossible dimensions, stretching endlessly into the distance like a boundless accordion of transportation. This is not merely a very long coach, longer than any vehicle that could exist in the physical world, but a boundlessly long one, its passenger compartments extending beyond any limited count, beyond any definite enumeration, beyond the very concept of length as we normally understand it. The coach carries a boundless number of passengers, each hoping to find accommodation at the famous Endless Lodge, each representing their own unique numerical perspective and research interest. For a moment, the supervisor feels the weight of what seems like an impossible request, a challenge that transcends even his growing expertise with boundless accommodations. How can a lodge that is already completely full accommodate not just some additional visitors, but boundlessly many additional visitors? The key insight comes when the supervisor realizes that he's been thinking too narrowly about chamber assignments, limiting himself to additive solutions when the true power of boundless arithmetic lies in its multiplicative properties. Instead of simply shifting visitors by adding the same number to each chamber, he can use multiplication to create gaps of boundless size within the existing chamber structure. This realization represents a crucial leap in numerical sophistication, the recognition that boundless sets can be partitioned and reorganized in ways that have no limited analogues. He makes a new announcement, his voice carrying a note of excitement as he prepares to implement a solution that seemed impossible just moments before. Attention current visitors, we hope you're enjoying your numerical explorations this morning. We have a boundless coach of visitors who would like to experience our establishment's unique properties. Please move to the chamber whose number is twice your current chamber number. This will create space for our new boundless collection of visitors while ensuring that everyone continues to enjoy the highest level of comfort and service. This elegant solution demonstrates the multiplicative structure of boundless arithmetic in action. The visitor in Chamber 1 moves to Chamber 2, taking with them their luggage and their numerical research materials. The visitor in Chamber 2 moves to Chamber 4, the visitor in Chamber 3 moves to Chamber 6, and so on throughout the boundless establishment. Every current visitor now occupies an even-numbered chamber, their new accommodations just as comfortable as their previous ones, their research and contemplation continuing uninterrupted in their new numerical environment. Meanwhile, all the odd-numbered chambers stand vacant, waiting to accommodate the boundless stream of new arrivals from the impossible coach. These odd-numbered chambers form a boundless set in their own right, perfectly matched to the boundless collection of new visitors who begin filing into the lodge with the patient efficiency of numerical objects taking their proper places in a logical structure. Each new visitor finds their accommodation exactly suited to their needs, their chamber number determined by their position in the boundless sequence of coach passengers. The beauty of this solution lies in its use of the fundamental properties of boundless set, principles that seem counterintuitive from a limited perspective, but reveal deep truths about the nature of numerical boundlessness. The set of even numbers is boundless, providing space for all existing visitors without any overcrowding or displacement. The set of odd numbers is also boundless, providing space for all the new arrivals from the boundless coach. Both sets have the same size as the complete set of positive integers, a fact that seems impossible from our limited perspective but is perfectly natural in the arithmetic of boundlessness. This is what number theorists call a one-to-one correspondence, a way of pairing elements from different sets that reveals they have the same cardinality, or size. Despite their apparent differences, the correspondence between the original visitor list and the even-numbered chambers demonstrates that a boundless set can be put into perfect correspondence with a proper subset of itself, something that's impossible with limited sets but routine with boundless ones. This property, known as Dedekind boundlessness, provides one of the most precise ways of characterizing what it means for a set to be boundless. This pairing principle opens up new ways of thinking about size and quantity that transcend our everyday experience with limited collections. In our ordinary experience, if one group is part of a larger group, the larger group must contain more elements, but in the boundless realm, a proper subset can have the same size as the whole set from which it's drawn, challenging our most basic intuitions about part and whole, container and contained. The even numbers are a proper subset of all positive integers, yet there are just as many even numbers as there are positive integers total. This counterintuitive fact illustrates why boundlessness requires its own special arithmetic, distinct from the limited arithmetic we use in daily life. The rules that govern limited quantities simply don't apply when we enter the realm of the boundless. Adding 1 to boundlessness doesn't make it larger. Doubling boundlessness doesn't change its size. These aren't arbitrary numerical conventions but logical necessities that follow from the definition of boundless sets and the principles of numerical reasoning. Understanding these principles requires letting go of limited intuitions and learning to think in terms of correspondences, mappings, and structural relationships.
As word spreads about the Lodge's boundless capacity, carried by academic networks and numerical journals to scholars around the world, the establishment becomes a destination for numerical pilgrims from across the theoretical landscape. Researchers arrive from universities and institutes worldwide, seeking to witness firsthand the strange properties of boundless sets that they've studied in abstract form for years. Each new challenge teaches the night supervisor more about the deep structure of numerical boundlessness, expanding his understanding of how boundless objects can be manipulated and reorganized according to logical principles. He begins to understand that boundlessness is not just about size, but about structure, pattern, and the elegant ways that numerical objects can be transformed and reorganized without losing their essential properties. The Lodge has become more than a place of accommodation. It's a laboratory for exploring the foundations of numerical thought itself, a place where abstract principles take on concrete form and theoretical insights become practical techniques. The supervisor finds himself at the center of a grand numerical experiment, learning through direct experience lessons that might otherwise require years of abstract study to master. The lodge's growing reputation attracts not just individual researchers but entire academic departments, numerical societies, and international conferences. Scholars come not just to experience the boundless accommodations but to conduct research, to collaborate on problems that require the kind of unlimited intellectual space that only a boundless establishment can provide. The lodge's common areas buzz with numerical conversation. Its boundless corridors echo with the excited discussions of researchers who have found in this impossible place a perfect environment for unlimited intellectual exploration. But just as the supervisor grows comfortable with boundless coaches, confident in his ability to handle any countably boundless collection of new visitors, he faces a challenge that will test the very limits of what seems possible, even in the realm of boundless accommodation. Looking out into the numerical landscape beyond the lodge, watching the dawn light illuminate the boundless horizons that surround his establishment, he sees not just one boundless coach, but a boundless parade of boundless coaches, each carrying its own boundless load of passengers, stretching back beyond any limited enumeration into a kind of numerical traffic jam that defies all conventional understanding. This is a scenario that would challenge even the most experienced number theorist: how to accommodate boundlessly many boundless groups of new visitors, each group boundless in itself, arriving simultaneously at an establishment that is already completely full. The supervisor realizes he'll need to think more systematically about the structure of boundlessness itself, to find patterns within patterns that can create order from what appears to be limitless chaos. This challenge will require him to move beyond the relatively simple techniques of shifting and doubling to explore more sophisticated methods of organizing boundless collections. The solution to this ultimate challenge requires the supervisor to think about boundlessness in a completely new way, transcending the linear thinking that served him well with limited and single boundless problems. Instead of working with individual chamber assignments or simple shifting patterns, he needs to create a systematic method for organizing boundlessly many boundless groups, a kind of boundless filing system that can bring order to what initially seems like hopeless complexity. The key insight comes from recognizing that he can organize all these passengers using a two-dimensional approach rather than the one-dimensional methods he's been employing. He pulls out what number theorists call a boundless matrix, a grid that extends boundlessly in both directions, like a vast spreadsheet that has no final row or column. This conceptual tool allows him to organize all the arriving passengers in a systematic way that makes their accommodation possible. Along the rows, he lists each boundless coach, Coach 1, Coach 2, Coach 3, and so on forever, each row representing one of the boundless coaches in the boundless parade. Along the columns, he lists the seat positions within each coach: Seat 1, Seat 2, Seat 3, and so on forever, each column representing a particular position that exists on every coach. Every passenger can now be identified by two coordinates: which coach they arrived on and which seat they occupied within that coach. The passenger from coach number 7, seat number 23, has a unique identifier that distinguishes them from every other passenger in the boundless collection. This systematic labeling transforms what seemed like an unmanageable chaos of boundless groups into an organized structure that can be systematically processed. The two-dimensional nature of the problem becomes manageable through the creation of a systematic coordinate system that captures the essential information about each passenger's origin.
The challenge now becomes one of mapping this two-dimensional boundless grid onto the one-dimensional boundless sequence of lodge chambers, a problem that initially seems impossible. How can you fit a two-dimensional boundlessness into a one-dimensional one? The question touches on fundamental issues in the study of boundless sets. Questions about whether different types of boundlessness might have different sizes, whether some boundless collections might be larger than others. At first glance, it seems like the two-dimensional grid should contain more elements than the one-dimensional sequence of chamber numbers. But the answer lies in a technique called diagonalization, a method that creates a systematic path through the boundless grid that eventually visits every position exactly once. The supervisor imagines drawing a path that starts at the top left corner of the grid, at the position representing coach 1, seat 1, and then zigzags back and forth across the grid in a carefully designed pattern. This path covers more and more of the grid with each sweep, systematically visiting positions in an order that ensures no passenger is overlooked, while avoiding any duplication in chamber assignments. First, He assigns Chamber 1 to the passenger from Coach 1, Seat 1, establishing the starting point for his systematic enumeration. Then Chamber 2 goes to Coach 1, Seat 2, and Chamber 3 to Coach 2, Seat 1, creating the first diagonal line across his boundless grid. Chamber 4 goes to Coach 3, Seat 1, Chamber 5 to Coach 2, Seat 2, and Chamber 6 to Coach 1, Seat 3, completing a triangular section of the grid. The pattern continues with each successive diagonal, sweeping across wider and wider sections of the boundless matrix while maintaining perfect systematic order. Continuing this zigzag pattern, the supervisor moves through successive diagonals of the grid, assigning chamber numbers in a systematic sequence that eventually reaches every passenger without exception. The passenger from Coach N, Seat M, receives a chamber number that can be calculated using a specific formula involving triangular numbers, ensuring that the assignment process is not just systematic but numerically precise. What seemed like an impossible organizational task becomes manageable through the systematic application of numerical structure, transforming chaos into order through the power of logical reasoning. This technique doesn't just solve the immediate problem, it reveals something profound about the nature of different types of boundlessness and how they relate to one another. The boundless parade of boundless coaches represents what number theorists call a countably boundless collection of countably boundless sets. The diagonalization technique proves that this two-dimensional boundlessness has the same size as the one-dimensional boundlessness of the Lodge chambers. This equivalence means that no matter how many boundless coaches arrive, as long as each coach carries only a countably boundless number of passengers, the endless lodge can accommodate them all. This diagonalization method has deep historical significance in numbers, representing one of the most important techniques in the study of boundless sets. It was first developed by the brilliant German number theorist Georg Cantor in the late 19th century, and it revolutionized our understanding of boundlessness in ways that continue to influence numerical research today. Cantor used similar techniques to prove that there are actually different sizes of boundlessness, some larger than others, a discovery that shocked the numerical world and led to the development of set theory. One of the foundational pillars of modern numbers, the Knight supervisor's solution to the boundless coaches problem is actually a practical application of Cantor's groundbreaking work on countable boundlessness, demonstrating how abstract numerical insights can be translated into concrete problem-solving technique. The zigzag pattern he uses to enumerate the passengers is essentially the same method that Cantor used to prove that the rational numbers are countable, that despite being densely packed on the number line, they can be systematically listed in a one-to-one correspondence with the natural numbers. With this technique mastered, the supervisor begins to understand something remarkable about the structure of numerical boundlessness that goes far beyond the practical problems of lodge management. The boundlessness represented by the natural numbers 1, 2, 3, 4, and so on, has the same size as the boundlessness represented by pairs of natural numbers, or by limited sequences of natural numbers, or by the rational numbers, or by any countably boundless collection of countably boundless sets. This type of boundlessness is called countable boundlessness, because its elements can be systematically counted off using the natural numbers themselves. It's the smallest type of boundlessness, yet it's already large enough to encompass all the visitors that could possibly arrive at the endless lodge through any conceivable series of limited or countably boundless coaches. This realization provides the supervisor with complete confidence in his ability to handle any accommodation challenge that involves countable quantities. No matter how complex the arrival pattern might be, the techniques he's developed form a complete system for managing countably boundless collections, applicable to any situation that involves only this type of boundlessness. But as the supervisor delves deeper into the study of boundlessness, working through late-night sessions of study and reflection in his office overlooking the boundless numerical landscape, he discovers that not all boundlessness types are created equal. The comfortable assumption that all boundless sets have the same size proves to be false, shattered by discoveries that reveal a rich hierarchy of boundless quantities with different properties and capabilities. One evening, as he's reviewing the lodge's visitor registration system and contemplating the elegant solutions he's developed for countable accommodation challenges, a new type of visitor arrives at his establishment. This visitor is different from all the others in fundamental ways that initially seem subtle but prove to be of profound numerical significance. Instead of having a simple numerical identifier like all previous visitors, this visitor's name consists of a boundless sequence of letters, each chosen from a set of just two possibilities, A and B. The visitor's name might begin A, B, A, B, A, B, A, B, and continue forever in some particular pattern, never reaching an end, never settling into a simple repetition, representing a boundless binary string that encodes information in ways that limited names cannot match. What makes this visitor special is that they represent not just one visitor, but an entire boundless coach full of passengers, each with their own unique boundless binary name. Every possible boundless sequence of A's and B's is represented among the passengers on this extraordinary coach, from the simple alternating pattern AB, AB, to the complex aperiodic sequences that never settle into any repetitive structure. The coach contains passengers whose names represent every conceivable way of making a boundless sequence of binary choices, every possible path through a boundless tree of decision points. The supervisor quickly realizes that this new challenge is qualitatively different from anything he's faced before, representing a type of boundlessness that transcends the countable realm he's mastered. Each passenger on this new coach has a name that's a boundless sequence of A's and B's, and there are uncountably many such sequences, more than can be systematically listed or counted using the natural numbers. This is what number theorists call uncountable boundlessness, and it's fundamentally larger than the countable boundlessness that the Lodge was designed to accommodate. The difference isn't just a matter of degree but of kind, representing a categorical distinction that cannot be bridged by any of the techniques the supervisor has learned, where countable boundlessness can be systematically enumerated, listed in a definite order that eventually reaches every element. Uncountable boundlessness resists all attempts at systematic enumeration. No matter how clever the counting scheme, there will always be boundless binary sequences that escape any limited description, that cannot be captured by any systematic procedure. The supervisor's previous techniques, elegant as they were for handling countable boundlessness types, cannot handle this new type of boundless visitor list. The shifting methods that worked for limited editions, the doubling technique that accommodated single boundless coaches, and the diagonalization procedure that handled boundless collections of boundless coaches, all depend on the countable nature of the collections they organize. When faced with an uncountably boundless collection, these methods reveal their fundamental limitations, unable to bridge the gap between countable and uncountable boundlessness. To understand why this new challenge is impossible to solve within the constraints of his Lodge, the supervisor employs a technique that Cantor developed called the diagonal argument, one of the most elegant and powerful proof methods in all of numbers. He imagines trying to assign chambers to all these visitors with boundless binary names, assuming for the sake of argument that such an assignment is possible. If it were possible, he could create a complete list pairing each chamber number with a unique boundless binary name, a systematic enumeration that covers every passenger from the boundless binary coach. But then the supervisor constructs a new boundless binary name, using a clever trick that reveals the impossibility of any such complete enumeration. For the first letter of this new name, he looks at the first letter of the first visitor's name and chooses the opposite letter. If the first visitor's name starts with A, the new name starts with B, and vice versa. For the second letter, he looks at the second letter of the second visitor's name and again chooses the opposite. For the third letter, he examines the third letter of the third visitor's name, and so on. Continuing this diagonal pattern through the supposedly complete list, he creates a new boundless binary name that differs from every name on his supposed complete list by at least one letter. The new name cannot be the first name on the list because it differs in the first position. It cannot be the second name because it differs in the second position. It cannot be the nth name for any value of n because it differs from that name in the nth position. This diagonal construction proves that any supposed complete list of boundless binary names must be incomplete. This diagonal argument proves that no complete list of boundless binary names can exist, because any such list would necessarily omit the diagonal name that can be constructed from it. Therefore, there are more boundless binary names than there are natural numbers to assign them to, more uncountably boundless passengers than countably boundless chambers. The supervisor has discovered the fundamental limitation of his Lodge. It can accommodate any countably boundless collection of visitors, but it cannot accommodate uncountably boundless collections. Some boundlessness types are indeed larger than others, and the Endless Lodge, for all its remarkable properties, cannot transcend the boundary between countable and uncountable boundlessness. This discovery leads the supervisor to reflect on the deeper philosophical implications of his numerical journey, implications that extend far beyond the practical problems of Lodge management. The Lodge, he realizes, is not just a clever puzzle about accommodating visitors, but a window into the fundamental structure of numerical reality. It demonstrates how numerical thinking can extend our intuitions into realms that seem impossible, yet reveals the precise boundaries of what remains possible even in those extended realms. The techniques he's developed for managing boundless visitors reflect real numerical methods that have profound applications in many areas of numbers and science. Consider, for instance, how the chamber shifting technique mirrors the way number theorists think about boundless series and sequences. When we want to insert a new term into a boundless sequence, we can shift all subsequent terms to make space, just as the lodge visitors shift to accommodate new arrivals. This technique appears in many areas of numerical analysis, from the study of convergent series to the manipulation of boundless products. The ability to insert elements into boundless structures without disrupting their essential properties is fundamental to many advanced numerical techniques. The technique of using even-numbered chambers for existing visitors and odd-numbered chambers for new arrivals reflects how number theorists partition boundless sets into boundless subsets, each maintaining the size of the original set. This kind of partition appears throughout numbers, from number theory where prime numbers and composite numbers form boundless subsets of the integers, to analysis where continuous functions can be partitioned into various boundless subclasses. Understanding how boundless sets can be decomposed and reorganized is essential for many areas of numerical research. These aren't just abstract curiosities or clever numerical games, they're fundamental tools used in analysis, topology, number theory, and many other numerical disciplines. The diagonalization technique that solved the boundless coaches problem has applications far beyond lodge management. It's used in computability theory to prove that some numerical problems are unsolvable, demonstrating that there are questions that no algorithm can answer regardless of how much time and computational power we might have. In logic, diagonalization is used to demonstrate the incompleteness of formal systems, showing that any sufficiently powerful numerical framework contains true statements that cannot be proven within that framework. In set theory, the same technique establishes the hierarchy of boundless cardinals, proving that there are boundlessly many different sizes of boundlessness, each larger than all those that come before it. What began as a whimsical thought experiment about lodge reservations connects to some of the deepest questions in numbers. What can be computed? What can be proven? What are the fundamental limitations of numerical systems themselves? These connections illustrate how numerical concepts weave together in unexpected ways, each discovery illuminating aspects of others in an endless network of logical relationship. As our night supervisor continues his contemplation, working through the implications of his discoveries during the quiet hours when the boundless lodge settles into its evening rhythm, he begins to see patterns connecting his establishment to other numerical paradoxes and puzzles that have challenged human understanding for centuries. The boundless binary names that his lodge cannot accommodate remind him of Cantor's famous proof that the real numbers are uncountable, a result that revolutionized numbers in the late 19th century. Just as there are more boundless binary sequences than natural numbers, there are more points on a line than natural numbers, more real numbers than integers. This connection between discrete sequences and continuous geometry illustrates how numerical concepts transcend the boundaries between different areas of study. The same boundlessness that appears in the analysis of boundless binary strings also appears in the study of continuous functions, the measurement of geometric objects, and the foundations of calculus. Numbers reveal themselves to be a unified enterprise where insights in one area shed light on problems in seemingly unrelated areas, where abstract set theory connects to concrete geometry, where discrete counting problems illuminate continuous measurement. The supervisor also recognizes connections to famous paradoxes in probability and decision theory that have puzzled number theorists and philosophers for generations. Consider, for instance, the St. Petersburg paradox, a gambling scenario where a game has boundless expected value but few rational people would pay even a modest amount to play it. Like the lodge's inability to accommodate uncountably boundless visitors, this paradox reveals limitations in our numerical models when extended to boundless cases, showing that boundlessness requires careful treatment and cannot simply be handled by scaling up limited methods indefinitely. Both situations demonstrate that boundlessness introduces qualitative changes in numerical reasoning, not just quantitative ones. The techniques that work perfectly well in limited contexts may fail completely when extended to boundless situations, requiring new approaches and new ways of thinking. This is why the study of boundlessness has been so important in the development of modern numbers, forcing number theorists to examine their assumptions carefully and develop more sophisticated tools for reasoning about unlimited quantities. Another connection emerges with Zeno's paradoxes of motion, those ancient puzzles about Achilles racing a tortoise and arrows that seem unable to reach their targets. Like the Lodge's boundless capacity, these paradoxes challenge our intuitions about how boundless processes can be completed in limited time. Zeno argued that motion is impossible because any journey must be divided into boundlessly many parts, each of which must be completed before the next can begin. How can boundlessly many tasks be completed in limited time? The resolution of Zeno's paradoxes required the development of numerical analysis and the precise study of boundless series, tools that weren't available to the ancient Greeks but became central to numbers during the 17th and 18th centuries. The same numerical techniques that resolve Zeno's paradoxes also illuminate the structure of the endless lodge, showing how boundless collections can be systematically organized and manipulated according to logical principles. The supervisor realizes that his lodge exists in the same conceptual space as these classical puzzles, a realm where numerical precision can resolve apparent contradictions while revealing deeper truths about the nature of boundlessness and continuity. The Lodge's accommodation strategies also connect to modern computer science and the theory of algorithms, fields that didn't exist when Hilbert first proposed his thought experiment but have become central to contemporary numbers and technology. The systematic methods the supervisor developed for assigning chambers mirror the recursive procedures that computer scientists use to process boundless or indefinitely large datasets. When a computer program handles a potentially boundless stream of data, it uses techniques similar to the Lodge's chamber assignment methods, systematically processing elements according to predetermined rules. The diagonal argument that proved some visitors cannot be accommodated parallels the undecidability results that show some computational problems cannot be solved by any algorithm, no matter how clever or powerful. Just as the Lodge cannot accommodate uncountably boundless collections of visitors, there are computational problems that cannot be solved by any limited procedure, questions that transcend the capabilities of any possible computer program. These limitations aren't due to technological constraints but to fundamental logical principles that govern what can and cannot be computed. The connection between the Lodge and computer science runs even deeper when we consider how modern computers actually work. Digital computers represent all information using limited sequences of binary digits, essentially limited versions of the boundless binary names that challenge the Lodge supervisor. The fact that uncountably boundless binary sequences cannot be systematically enumerated has direct implications for what kinds of information can be represented and processed by digital systems. The theoretical limitations discovered through thought experiments like the Endless Lodge translate into practical constraints on real computational systems. As the supervisor's understanding deepens through these connections and contemplations, working through problems during the quiet hours when the Lodge's boundless corridors echo with the gentle sounds of numerical research and scholarly discussion, he begins to appreciate how the Lodge serves as a bridge between abstract numerical theory and practical problem-solving techniques. The same mental flexibility required to see how a full Lodge can accommodate new visitors is needed to understand how numerical systems can be extended and generalized beyond their original domains. The willingness to abandon limited intuitions in favor of boundless reasoning mirrors the kind of conceptual leaps that drive numerical progress in many fields. When number theorists developed calculus, they had to learn to work with infinitesimal quantities that challenged conventional notions of number and measurement. When they developed non-Euclidean geometry, they had to abandon the assumption that Euclid's parallel postulate was necessarily true. When they developed abstract algebra, they had to generalize familiar operations to work with objects that didn't behave like ordinary numbers. Each of these developments required the same kind of conceptual flexibility that the Lodge supervisor displays when he learns to think about boundless accommodations. The ability to extend familiar concepts into unfamiliar domains, to follow logical reasoning even when it leads to counterintuitive conclusions, to see new possibilities within apparently constrained situations. This flexibility is perhaps the most important skill in numerical thinking, more valuable than any particular technique or result. The story of the Endless Lodge also illuminates the historical development of numerical ideas about boundlessness, showing how concepts that seem natural and obvious to us today were once revolutionary and controversial. For centuries, number theorists were uncomfortable with boundless quantities, viewing them as potential rather than actual numerical objects. The ancient Greeks, despite their geometric sophistication and logical rigor, struggled with boundless processes and avoided dealing with completed boundlessness whenever possible. Medieval scholars debated whether boundless quantities could exist in reality or only in the mind of God, treating boundlessness as a theological rather than a numerical concept. Renaissance number theorists began to work with boundless series and boundless products, but they were often unsure about the legitimacy of their methods and results. It wasn't until the 19th century that number theorists like Cantor developed rigorous methods for working with boundless sets as legitimate numerical objects, establishing the foundations for modern set theory and numerical analysis. Cantor's work initially faced fierce resistance from the numerical establishment, illustrating how revolutionary ideas often challenge existing assumptions and institutional structures. His mentor, Leopold Kronecker, famously declared that God created the integers, all else is the work of man, reflecting a belief that boundless sets were illegitimate numerical constructions that went beyond the proper boundaries of numerical reasoning. Henri Poincaré, one of the greatest number theorists of his generation, called Cantor's set theory a disease that numbers needed to cure rather than embrace. Yet these revolutionary ideas gradually gained acceptance as number theorists recognized their power and elegance, their ability to resolve long-standing paradoxes and open up new areas of research. What seemed like abstract philosophical speculation proved to have practical applications in many areas of numbers and science. The techniques that Cantor developed for working with boundless sets became fundamental tools in topology, analysis, logic, and many other numerical disciplines. The resistance to his ideas illustrates how numerical progress often requires overcoming not just technical difficulties but conceptual and institutional barriers. The Knight supervisor's journey mirrors this historical progression from confusion to clarity about boundless quantities, from mechanical technique to deep understanding. His initial solutions seem like clever tricks, responses to particular challenges that arise in his unusual establishment. But as he masters the underlying principles and begins to see the connections between different techniques, he develops genuine insight into the structure of boundless sets. This progression from mechanical technique to deep understanding reflects how numerical knowledge develops both in individuals and in the numerical community as a whole. The Lodge also provides a gentle introduction to some of the most profound questions in the foundations of numbers, questions that continue to occupy researchers today and may never be completely resolved. The distinction between countable and uncountable boundlessness leads naturally to questions about the continuum hypothesis, one of the most important unsolved problems in set theory and one of the famous Hilbert problems that David Hilbert himself identified as central to numerical progress. The continuum hypothesis concerns whether there are any boundless sets whose size lies strictly between the countable boundlessness of the natural numbers and the uncountable boundlessness of the real numbers. Cantor believed that no such intermediate boundlessness types exist, that the real numbers represent the next size of boundlessness after the natural numbers. But despite decades of effort by some of the world's greatest number theorists, no one could prove or disprove this hypothesis using the standard axioms of set theory.
In one of the most surprising developments in 20th century numbers, Kurt Gödel and Paul Cohen proved that this question is independent of the standard axioms of set theory, meaning it can neither be proved nor disproved within the usual numerical framework. This independence result shows that the continuum hypothesis is undecidable within standard numbers, similar to how the parallel postulate is independent of the other axioms of Euclidean geometry. The question of intermediate boundlessness types remains open, not because we haven't been clever enough to solve it, but because it transcends the logical system we use to ask it. This independence result connects to Gödel's even more famous incompleteness theorems, which show that any sufficiently powerful numerical system contains true statements that cannot be proved within that system. The Lodge's inability to accommodate certain types of boundless visitors serves as a gentle metaphor for these fundamental limitations in numerical systems. Just as the Lodge has absolute constraints despite its boundless capacity, numerical systems have absolute limitations despite their tremendous power and scope. These limitations aren't flaws or temporary obstacles but fundamental features of logical systems that reveal deep truths about the nature of numerical reasoning itself. They show that numbers, for all their precision and rigor, cannot achieve complete self-contained certainty, that there will always be questions that transcend any particular numerical framework. This recognition has led to new areas of research in logic and foundations, new ways of thinking about the relationship between numerical truth and numerical proof. The supervisor's experience also touches on questions in numerical philosophy about the nature of numerical objects themselves, questions that philosophers and number theorists have debated for centuries without reaching consensus. Are boundless sets like the Lodge's visitor list real entities that exist independently of human thought? waiting to be discovered by numerical exploration? Or are they merely useful constructions that help us organize our thinking about numerical relationships? Tools that work well for certain purposes without necessarily corresponding to any external reality. Different philosophical schools offer different answers to these questions, each with its own strengths and weaknesses. Platonic realists argue that numerical objects exist in an abstract realm of perfect forms, independent of physical reality but accessible to human reason through numerical investigation. Formalists argue that numbers are essentially a sophisticated game played with symbols according to precise rules, meaningful only within the context of particular formal systems. Constructivists insist that numerical objects must be explicitly constructed using limited procedures, rejecting boundless objects that cannot be built through step-by-step processes. The Lodge's practical usefulness in solving accommodation problems suggests that boundless sets, whether real or constructed, capture something important about the logical structure of numerical reasoning. The techniques that work in the Lodge context also work in many other numerical situations, suggesting that they reflect genuine patterns in the logical relationships between numerical concepts. Whether these patterns correspond to external reality or emerge from the structure of human reasoning itself remains an open question. But regardless of one's philosophical position on the ultimate nature of numerical objects, the Lodge demonstrates the practical value of working with boundless concepts in numerical problem solving. The same techniques that allow the supervisor to accommodate boundless visitors also allow number theorists to solve problems in analysis, topology, number theory, and many other areas. The conceptual tools developed for understanding boundless lodges have applications far beyond their original context, illustrating the practical power of abstract numerical thinking. As the night settles deeper around our numerical lodge, with its boundless corridors softly lit and its countless visitors settled into their comfortable accommodations, the supervisor finds himself contemplating the aesthetic dimensions of his work. There's something deeply beautiful about the way boundless patterns unfold, the way systematic procedures can create order from apparent chaos, the way simple rules can generate unlimited complexity. The visitor arrangements that initially seemed impossible become elegant once the proper perspective is achieved, revealing hidden structures that were present all along but invisible until illuminated by numerical insight.
This aesthetic appreciation is central to numerical experience. The sense that numerical truth is not just correct but beautiful, not just functional but elegant. Number theorists often speak of the beauty of a particular proof, the elegance of a theoretical framework, the surprising connections that link apparently unrelated areas of study. This aesthetic dimension isn't mere decoration but seems to be connected to numerical truth itself, as if beauty serves as a guide toward deeper understanding. The beauty of the Lodge's solutions lies partly in their economy of means, their ability to achieve complex results through simple and systematic methods. The same basic techniques, systematic enumeration, one-to-one correspondence, diagonalization, solve a wide variety of seemingly different problems. This economy reflects a deeper numerical principle. The most powerful numerical tools are often the most general ones, applicable across many different contexts and problems. The night supervisor's methods work not because they're specifically designed for Lodge management, but because they capture fundamental patterns in the structure of boundless sets. This generality also explains why the Lodge paradox has remained popular among number theorists and education specialists for nearly a century. It's not just a clever puzzle or an entertaining thought experiment, but a gateway to understanding some of the most important concepts in modern numbers. Students who master the Lodge's accommodation strategies have taken their first steps toward understanding real analysis, set theory, computability theory, and many other advanced numerical topics. The paradox serves as a bridge between intuitive thinking and formal numerical reasoning, making abstract concepts accessible through concrete imagery. The Lodge's enduring appeal also stems from its concrete imagery, the way it transforms abstract numerical concepts into vivid and memorable scenarios. The boundless coaches and chamber assignments provide tangible anchors for ideas that might otherwise remain frustratingly ethereal. This pedagogical power of concrete metaphors reflects an important aspect of numerical thinking, the ability to move fluidly between abstract concepts and concrete representations, using each to illuminate the other. Numerical abstraction and concrete representation aren't opposed but complementary, each contributing essential elements to numerical understanding. Abstract thinking allows us to see patterns that transcend particular examples, to develop techniques that apply across wide ranges of problems. Concrete representation helps us understand what abstract concepts mean, provides intuitive anchors for complex ideas, and suggests new directions for theoretical development. The best numerical thinking combines both approaches, using abstraction to achieve generality and concreteness to maintain contact with experience. The supervisor's work also illustrates another important aspect of numerical thinking, the iterative nature of problem solving and understanding. His initial solutions to accommodation challenges were somewhat mechanical, following procedures without deep comprehension of why they worked. But as he encountered more complex situations and began to see connections between different techniques, his understanding deepened and became more sophisticated. This progression from technique to understanding to insight is characteristic of numerical learning at all levels, from elementary arithmetic to advanced research. Numerical understanding develops through a kind of spiral process, revisiting the same concepts at deeper levels of sophistication. A student might first learn about boundlessness as going on forever, then encounter boundless sets in more formal contexts, later study the technical properties of different types of boundlessness, and eventually contribute to research on foundational questions about boundless objects. Each level of understanding builds on previous ones while opening up new questions and possibilities. The Lodge provides an excellent example of this spiral development, accessible enough to engage students at introductory levels while containing enough depth to support advanced study and research. The basic accommodation problems can be understood with elementary numerical background, while the deeper questions about countable and uncountable boundlessness connect to sophisticated areas of contemporary numbers. This multi-level accessibility makes the Lodge paradox a particularly valuable pedagogical tool. As our exploration nears its conclusion, the Night Supervisor reflects on how his extraordinary Lodge has changed his understanding of numbers itself and his role within the numerical community. What began as a simple puzzle about chamber assignments has opened up vistas of boundless complexity and beauty, connecting him to traditions of numerical thinking that stretch back centuries and forward into areas of active contemporary research. He's learned that numbers are not just about calculating correct answers, but about recognizing patterns, questioning assumptions, exploring possibilities, and discovering connections between seemingly unrelated ideas. The Lodge has also taught him about the importance of precise thinking in numbers, the way that careful attention to definitions and logical relationships allows numerical reasoning to achieve certainty and generality that would be impossible through informal methods. The difference between countable and uncountable boundlessness isn't just a technical distinction or an abstract philosophical curiosity. It's a fundamental divide that determines what's possible and what isn't in many areas of numbers and science. Numerical precision isn't pedantic nitpicking, but the careful attention to detail that allows us to navigate reliably through conceptual territories where intuition alone might lead us astray. Perhaps most importantly, the Lodge has illustrated how numerical thinking can expand our sense of what's possible, both within numbers and in our broader understanding of logical reasoning and problem solving. The techniques that seemed impossible in limited contexts become routine in boundless ones. Problems that appear unsolvable yield to systematic methods when approached from the right angle. Apparent contradictions resolve into deeper understanding when examined with sufficient care and precision. This expansion of possibility is one of numbers' greatest gifts to human culture, the demonstration that careful reasoning can transcend the limitations of immediate experience and reveal new realms of understanding. Numbers show us that there are more things possible than we might initially imagine, more ways of thinking than we encounter in everyday life, more connections between ideas than appear on the surface. These discoveries don't just advance numerical knowledge but expand human intellectual capacity more generally. The Night Supervisor's story also reflects the way numerical understanding develops through practice and reflection, through engagement with concrete problems and abstract principles. His initial solutions were somewhat mechanical, following procedures without full comprehension of their underlying logic, but as he encountered more complex challenges and began to see the connections between different techniques, he developed genuine insight into the structure of boundless sets and the principles that govern their manipulation. This progression from technique to understanding to insight is characteristic of numerical learning at all levels, from elementary arithmetic to advanced research. It requires both persistent effort and creative imagination, both logical discipline and openness to unexpected possibilities. The Lodge provides an ideal context for this kind of learning because it combines concrete imagery with abstract principles, practical problem solving with theoretical understanding. The Lodge serves as a reminder that numbers are fundamentally a human enterprise, driven by curiosity, creativity, and the desire to understand. The problems that arise in managing boundless visitors may seem abstract or removed from practical concerns, but they reflect real questions that have puzzled and inspired number theorists for generations. The solutions that work have been discovered by real people, often through combinations of logical reasoning, creative insight, and persistent effort that required years or decades to achieve. Behind every numerical concept stands a community of researchers who have contributed to its development, refined its formulation, explored its implications, and connected it to other areas of numerical knowledge. The Lodge paradox draws on work by Hilbert, Cantor, and many other number theorists who have contributed to our understanding of boundless sets. Their individual contributions have combined to create the rich theoretical framework that makes the Lodge's accommodation strategies possible. As we prepare to check out of our endless Lodge, it's worth noting that the paradox continues to generate new insights and applications across many areas of numbers and science. Modern number theorists use Hilbert-style arguments in context ranging from computer science to physics to economics. The fundamental techniques of enumeration, correspondence, and diagonalization remain active tools in contemporary numerical research, appearing in work on everything from artificial intelligence to quantum mechanics to financial modeling. What seemed like a whimsical thought experiment has proven to have lasting significance for numerical understanding and practical problem solving. This connection between playful imagination and serious research is characteristic of numbers, where the most abstract and seemingly impractical ideas often turn out to have unexpected applications. The Lodge reminds us that numerical thinking benefits from a spirit of curiosity and exploration, a willingness to follow ideas wherever they lead without worrying too much about immediate practical applications. The Lodge also reminds us that numbers are ultimately about patterns and relationships rather than specific figures or calculations, about structure and logic rather than particular content. The particular chamber assignments matter less than the systematic methods for creating them. The specific coach flows matter less than the general principles for accommodating them. This focus on structure over specifics is characteristic of numerical thinking and explains why numerical insights often apply far beyond their original context. This structural focus allows numerical knowledge to be cumulative and transferable in ways that would be impossible if numbers were primarily about memorizing facts or procedures. When you understand the underlying logic of boundless accommodation, you can apply that understanding to new situations that might seem completely different on the surface. When you master the technique of diagonalization, you can use it in contexts far removed from Lodge management. This transferability makes numerical education particularly valuable as preparation for dealing with novel and complex problems. The Lodge's story also illustrates the social and collaborative nature of numerical understanding, the way that individual insights build on previous work and contribute to collective knowledge. The Knight supervisor's solutions draw on techniques developed by many number theorists over many generations, refined through countless applications and extensions. His work, in turn, might inspire new approaches to boundless problems that could benefit other number theorists and other areas of research. This collaborative aspect of numbers is sometimes overlooked in educational contexts that emphasize individual problem solving and competitive achievement. But numerical progress has always been fundamentally social. Depending on communication between researchers, critical evaluation of proposed solutions, and the gradual accumulation of validated techniques and results. The Lodge provides an excellent context for collaborative learning, where students can work together to develop accommodation strategies and explore their implications. Tonight, as you drift towards sleep, perhaps you'll carry with you some sense of the boundless possibilities that numbers reveal, not just in the abstract realm of pure thought, but in the practical world of problem solving and understanding. The Endless Lodge may exist only in the realm of numerical imagination, but it illuminates real features of logical reasoning that apply to many areas of human experience. In the gentle space between waking and dreaming, where limited minds contemplate boundless possibilities, there's something beautiful about knowing that such elegant paradoxes exist, even if we can never actually check into the Lodge ourselves. The techniques and insights developed through studying the Lodge have applications in computer science, where algorithms must handle potentially boundless data streams. They appear in physics, where boundless series are used to model continuous phenomena. They arise in economics, where models may involve boundlessly many agents or boundlessly many time periods. They emerge in biology, where boundless populations provide useful approximations for understanding evolutionary dynamics. These applications show that the Lodge is more than just an entertaining puzzle or a pedagogical device. It's a window into numerical techniques that have become essential tools for understanding and modeling complex systems across many fields of human knowledge. The abstract thinking required to master boundless accommodation translates into practical skills for dealing with complex problems in science, technology, and other areas where systematic reasoning is essential. The Night Supervisor's story continues, of course. Beyond the challenges we've explored together, there will always be new types of visitors arriving at the Lodge, new accommodation problems to solve, new connections to discover between different areas of boundless numbers. But he faces these future challenges now with the confidence that comes from understanding boundless arithmetic, with tools that can handle any countably boundless challenge, and with the wisdom to recognize the boundaries that even boundless thinking cannot cross. His Lodge remains forever full and forever ready for more visitors, a testament to the strange and wonderful arithmetic of boundlessness. The visitors continue their numerical research and collaboration in their boundless accommodations, contributing to the ongoing development of human understanding. The Lodge serves as a symbol of numbers itself, always growing, always discovering new possibilities, always pushing against the boundaries of what seems possible while respecting the logical constraints that make numerical reasoning reliable and powerful. And so our gentle journey through the study of endless possibilities draws to a close, though like any good numerical exploration, it raises more questions than it answers and opens up more avenues for investigation than it closes. Whether you're a seasoned number theorist who has worked with boundless sets for years or someone encountering these ideas for the first time, I hope you found something thought-provoking in the Lodge's impossible geometry and elegant solutions. Numbers offer many such paradoxes and puzzles, each one a doorway into deeper understanding of the logical structures that underlie our universe. The Endless Lodge stands as a monument to human curiosity and ingenuity, to our capacity for abstract thinking and logical reasoning, to our ability to imagine possibilities that transcend immediate experience and discover truths that illuminate the fundamental nature of numerical reality. It reminds us that numbers are both a practical tool for solving problems and a source of beauty and wonder, both a precise language for describing relationships and a playground for intellectual exploration. As your own limited mind settles into rest, remember that you've spent time contemplating boundlessness itself, wrestling with concepts that have challenged the greatest numerical minds in history, and perhaps gaining some appreciation for the beauty and power of numerical thinking. The Endless Lodge will continue operating through the night, its impossible chambers forever ready to accommodate whatever numerical travelers might arrive in your dreams, its elegant solutions continuing to illuminate the strange and wonderful arithmetic of endless possibilities. Sleep well, and may your rest be filled with the gentle arithmetic of boundless possibilities, where every problem has a solution and there's always room for one more beautiful idea. In the quiet hours of the night, as consciousness fades and the boundaries between the limited and boundless begin to blur, perhaps you'll find yourself a visitor in that impossible lodge, exploring numerical landscapes that stretch beyond any horizon, discovering patterns and connections that exist nowhere else but in the boundless realm of numerical thought. The lodge's lights will stay on through the night, not because they need to illuminate boundless corridors for the practical purpose of navigation, but because they represent the light of human understanding, the illumination that numbers bring to dark corners of confusion and uncertainty. In that light, impossible problems become routine accommodations, paradoxes resolve into deeper insights, and the boundless reveals itself to be not just numerically fascinating but surprisingly practical, not just logically consistent but aesthetically beautiful. Tomorrow there will be new numerical challenges to explore, new boundless accommodations to arrange, new connections to discover between the abstract realm of pure numbers and the practical world where we apply numerical insights to solve real problems. But for now, in the gentle darkness of approaching sleep, it's enough to know that such wonders exist, that human minds can comprehend boundless possibilities, and that numbers offer a permanent invitation to explore realms of thought that expand our understanding of what's possible in both logical reasoning and creative imagination.